Welcome back to Office Hours with Dr. Clark. Today we are going to be looking at the mole concept some more. We're going to be looking at percent composition, empirical, and molecular formulas. Open up my whiteboard here. We'll get started. Okay, so let's talk about percent composition. Let's say we have sodium carbonate. We want to find the percent of sodium. So first, we have to find the molar mass of sodium carbonate. So sodium is 23, so that's 2 of that, plus 12, that's carbon, plus 3 times 16, that's oxygens, for a total of 106 grams per mole. So we have to really know our chemical formulas in order to really do well in these types of questions. So now, according to our formula, percent of Na is going to be the molar mass of sodium times 2 over the molar mass, this is grams, molar mass, oops, the molar mass of the overall compound. Right? So that's a formula times 100. So depends on how many of the element is in the compound, that's where this number comes in. So if it was oxygen, this number would have been 3, and this would have been the molar mass of oxygen. So when we do the math, and then that's going to be 43%. So I'll match the sig figs to the sig figs for the sodium. I ignore the 2 because that's not that's just a counting number. So that's how we do percent composition. What about, let's say we want to do percent composition for percent of C and CH4O. So we have to find the molar masses first. That's 12 plus 4 times 101 for the hydrogen, plus 16 for the oxygen. That's grams. You add that up. That's 4 times 1.0. 4 times 1.01 plus 12 plus 16. So 32.04 grams per molar mass. So our percent of C is equal to 12 times 1. There's only 1 carbon in there, divided by 32.04 grams. So it's grams and times 100. Can't forget that part. So essentially, 12 divided by 32.04 times 100. So it gives me 37% of carbon in CH4O. So one use of percent composition is enabling us to find empirical and molecular formulas. Let's say, for example, I have 76.0% of C 12.8% H and 11.2% O in some compound, right? A compound is contains carbon, hydrogen, oxygen. And it was found that the molar mass, which we can, without even knowing what the compound is, it was equal to 284 grams per mole. What is the empirical and molecular formulas? Okay. So the first thing you want to do, you want to assume 100 grams. So what that does is that converts all those percentages to grams. So 76% of 100 is 76 grams. So therefore my carbon is 76.0 grams. H is 12.8 grams and O 11.2 grams. So now I have grams, I gotta convert that to those to moles. So moles of C, 76.0 grams, divided by the molar mass of carbon is 12.0 grams. And actually, well, let me do it in terms of, let's do it in terms of conversions. So that we're always centering that habits. All the C. These calculations, they're not hard calculations, but they're time consuming. But you have to go through the steps. You have to be systematic about it. So 12.8 grams times 1 molar mass of hydrogen. Then O, 11.2 grams. 16 grams. So I like to set my up. Let's be very systematic, lay everything out, do my math. So the carbon, so I always like to keep at least 4 sig figs for my moles. The reason why we want to do that is we don't want to start rounding too early because you can end up with some wonky answers. So we always want to give as many sig figs as possible. So then now we're told with empirical formulas, so you want to divide each of these moles by the smallest number of moles. So that's going to be seven, divide this by 0.7, and divide this by 0.7. So 6.333 divided by 0.7. Oops. Is 9. This is 9.0, which you can safely call 9. And then 12.67 divided by 0.7 is 18.1, which we can call 18 without any issues. And then we have 1. Right? So my empirical formula is C9H18O. Okay. This is my empirical formula. So remember, the empirical formula just tells you the ratio of all the atoms to each other. It doesn't tell you any more information than that. So this is not the actual formula for the compound. It just tells me that there's twice as many hydrogens as there's carbon in the compound. And there's only relative to the carbon and the hydrogen, we're going to have one. So it's a 9 to 18 to 1 ratio of these atoms. So now we're told that the molar mass of the compound, using a separate determination, they found it to be 284.5 grams. So first I got to find the molar mass of the empirical formula. Mass of the empirical formula, that's 9 times 12 plus 18 times 1.01 plus 16.04. Page. $18.18 plus 16. So then I just define my multiplier n. I divide the molar mass given divided by the molar mass of the empirical formula that's calculated, and it's around 2. So now I take my C9H18O and I multiply those subscripts by 2, end up with C18H36O2. And that's my molecular formula. So it's a few steps, right? But it's pretty systematic. You're given percent composition, you immediately, essentially, just remove the percentage and replace them with grams, right? Because we're assuming 100 grams of compound. And then you find your moles of each, like you've done before. Grams divided by molar mass will give you moles. And then divide by the smallest number of moles. And you want to round to whole numbers, right? So your ratios here should be whole numbers. And then you write your empirical formula. And if you're given information about the molar mass, you can find a molecular formula by adding up finding the molar mass of the empirical formula, which in this case is 142.18, dividing the molar mass given by this molar mass that we just calculated. And you should get some whole number multiplier, and multiply these subscripts by the whole number, and you will get the molecular formula. So that's how we deal with percent composition, the first thing we did, and find the empirical and molecular formula. All right, so join me next time for Office Hours with Dr. Clark.